Hello and welcome to the lesson on the 7 characteristics of a sound wave. I'm going to start this video by kind of explaining why you would need to know the 7 characteristics of a sound wave. First of all, if something doesn't sound right, if you're mixing and something just sounds off, something sounds thin, maybe the bass and the kick drum are fighting each other, maybe it's too loud, maybe there's some irritating frequency floating around, maybe this is causing someone discomfort or pain, or it just generally sounds dull or bad, it's usually going to come down to one or more of these 7 characteristics of a sound wave. So let's jump right into it. So the 7 characteristics are frequency, amplitude, timbre, envelope, velocity, wavelength, and phase. So let's talk about frequency. So frequency is the rate or the time it takes for a sound wave to complete one cycle. And this is what one cycle looks like. From this point A to this point B is one cycle, and this is a representation of what a sine wave would look like. So if you think of waves on the beach, frequency is how fast the waves hit the beach. It's the time it takes from one wave to hit the beach until the next wave hits the beach. The faster the waves hit, the higher the frequency. And I'm going to start right here. Stop right here for a second and say from 20 hertz to 20,000 hertz is the general range of human hearing. And we're going to talk about hertz in a second here. So just like the speedometer on a car, we can measure the speed or the frequency of the waves. And sound waves are very specific in their frequency. And this is called hertz, which is cycles per second. So hertz is actually the pitch or the note the wave is producing also. A 440 hertz cycle is basically the note A. A 440 hertz tone is repeating 440 times per second. Amplitude is number 2, and it is simply the intensity, volume, or loudness of a sound wave. So in frequency, I mentioned that waves in an ocean, if frequency is the rate at which the waves come in, then amplitude is the height of the waves. The bigger or higher the wave, the louder it is. The smaller or shorter the wave, the softer it is. Even inside the sound wave itself, you can have different amplitudes. So when I was in Nashville, we used to record everything to 2-inch tape, Studer machines. And you could actually see the sound wave on that tape. If you took a little magnifying glass, you could see the sound wave. And it was actually kind of a really cool thing to see. And the broader and bigger the sound wave was, the louder it was. The shorter it was, the softer it was. So timbre. Timbre is pronounced timbre, not timber or timbre or timbre or whatever. It's timbre. And timbre is basically the flavor of the sound or the color of the sound that makes it identifiable and unique to its source. Source being the instrument or the vocal. For example, you can play the same note on a piano, a clarinet, and a trumpet, but they will all sound different, and they will all have their very unique individual flavor that distinguishes them from other instruments. So how can this be? In frequency, we learned that the cycle is specific to the note. The cycle is specific to the note. This is a very true statement. However, there are other tones that are introduced when the fundamental note is played. A fundamental note is the primary frequency, like 440 hertz. However, there are also overtones and subtones that give a source its unique flavor. This is because every note or frequency does not live in an isolated manner. And what this means is that there are resonating tones that also get into the mix. So if you think back on that sine wave, the constant curve, okay, well, that, if it's a 440 hertz, that one cycle is a sine wave. Well, there are different shapes of waves, but they can still be that same cycle, that same note. So if you can put notches or, waves or, jagged edges on that constant curve, that can change the sound or the timbre of that whatever's producing the sound. So when I was talking about back in Nashville, when I would look at the 2-inch tape, I could see all the instruments playing the same note, but all the sound waves looked different even though the cycles were the same. So the frequency was the same. The cycles per second were the same. But the hertz were the same, but the shape of the sound waves were completely different. And that's where sound becomes really interesting. So here's an experiment. I want you guys to try this. After I explain it, just sit down and try doing this. Sit at an acoustic piano and then just hit one note. Bing. You will hear other notes, overtones, and subtones also. Plus, you will hear the fundamental octaves above and under the note you played. The unique sound that the piano is producing lets you recognize that it is a piano. And this is what's called timbre. Envelope. Envelope is a fun one, and it's kind of it sounds complicated, but it's actually kind of the easiest one. The envelope is actually 4 different characteristics rolled into one. Sometimes it's called ADSR or an ADSR envelope. That's because ADSR stands for something. It stands for attack, decay, sustain, and release. So think of it as 4 different sheets of paper that you fold up and put into an envelope and then drop in the mail. It's actually 4 things in one, 4 things in the envelope. So the first one is called attack. And the attack is how fast the wave takes to reach its loudest moment. Now you'll know its loudest moment because you'll either hear it, or if you can see the sound wave, it'll be taking up the most space. For example, if the source takes longer to reach its peak, then it is considered a slow attack. If the source reaches its peak quickly, it is considered a fast attack. Now, a violin with a bow drawn across it usually has a slower attack, while a snare drum whack is a fast attack. This is very important to understand and know when you are using compressors, gates, and effects. Actually, the envelope itself, all 4 of them, are very important to know when using compressors, gates, and effects. So decay is the second one. So the decay is simply the amount of time it takes for the wave to reduce in amplitude until it enters into the sustain phase of the envelope. Again, it's very important to know when using gates and compressors. So you have the attack, boom, to the loudest point, and then from the loudest point down to where it enters sustain, you have what's called the decay. So guess what the next one is? Sustain. After decay, the waves enter what is called sustain. And sustain is simply an even sound level over a period of time until it reaches the release, which is the R of the ADSR. And the release is basically the time it takes for the wave to end once the note has stopped playing. Imagine a piano again. If you hit the key, there is a definite point at which the note stops sustaining and starts to end. When it is silent, the wave has been released. So let's move on to what comes on after envelope, which is called velocity. Velocity is basically the speed the wave travels. Yes, the cycles are the same, but it moves through the air at different speeds. This is measured in feet per second. Traditionally, the higher the frequency, the faster the wave travels. However, a wave's velocity is subject to many things like humidity, temperature, and altitude. And then I'm going to interject here also, like if you're doing a rehearsal and it sounds really good and the room is empty, when people fill up the room, it's gonna change a lot of the sound, especially on the lower mid-range end. So just be aware of that. Velocity is an extremely important thing to be able to determine when mixing live, and this is a very true statement, as many effects and dynamics are dependent upon velocity. Wavelength. Number 6, wavelength. Wavelength is the distance from the beginning of the sound wave until the release has occurred. This is important to know when timing subs or line arrays or timing speakers to each other and stuff like that. What is the wavelength? What is the time and the distance from the beginning of the sound wave until the release has occurred? So this is an example of a sound wave. And if you look over here, the wavelength, that's the beginning where that red circle is, and it goes all the way over to here where it ends. That is the wavelength. This area right here is building up, and this is the attack right here. This area right here is the attack. More specifically, this area right here. Okay. This area, you see how it's coming down and it's coming in? Okay, this area right here is the decay. Okay. This area right here after the decay is the sustain. Here's the sustain right here, is keeping a pretty level amplitude through time. And then right here is starting to dwindle to the release. And this is considered the release right here, boom, when it ends. And that is the release. And now we will move on to number 7 of the characteristics of a sound wave, and that is phase. So phase is kind of hard to define, so here's my best shot. Sound waves form in regular cycles, like we were talking about before, like 440, 880, whatever the cycle is. So phase is basically how far into that cycle the wave is. Phase is measured in degrees, so 360 degrees is one cycle. Now, if you think about it, that sine wave that I had earlier, the half circle and the half circle, if you put those two together, that's basically 360 degrees. And if you can do that, you can do that halfway through a cycle, divide it in half and put them together, and you've got 360 degrees no matter what kind of wave you have. The reason phase is such a big deal is because there can be what's called phase cancellation or cancellation between waves. And one of the things you're going to be doing as an audio engineer the most is making sure that everything is as close to phase as possible. One thing I'm going to talk about phase is this. If you have what's considered completely out of phase or phase cancellation, people call it out of phase, you basically have eliminated the sound. The more out of phase, if they're 100% out of phase, you have zero sound. So if you have 1 minus 1, 0. Now, the other is true too. If you have two waves that are completely in phase with each other, that's 1 plus 1. You actually doubled its amplitude. So as stated before, there are different degrees of phase cancellation. A complete phase cancellation produces silence because the waves are in identically opposite cycles. They cancel each other out. They are 180 degrees out of phase and completely cancel each other out. Imagine in your head a wave going up in cycle. Now imagine a mirrored image of that with the wave going below in the cycle at the same time. You will actually cancel that sound out. The more out of phase the subsequent sound waves are, the more hollow or thin they will sound. That is very true. So let's say you're 80% out of phase. Okay, and then we're going to talk about the phase button here for a second. And then you can flip it over to only 20% out of phase if you hit the phase button. And all of a sudden, everything just sounds better. So phase will usually occur when you have two mics on one source. Phase will usually occur when you have two mics on one source, as in a kick mic, in mic, and a kick out mic. Usually next to the mic pre or the gain knob on your mixer, there is a phase button, and it looks like a 0 with a line through it. If you suspect that the two mics are out of phase, you can press that button on one of them and switch the phase on one of the mics. If it sounds richer and fuller, keep it. If it sounds thinner and more hollow, then switch it back. Now, here's the thing. If you've been messing with phase on your microphones and it's still, no matter what you do, sounds wonky, you need to move one of the mics or both of the mics into a better position. The better mic you get at mic placement and the better you get at phase, the more awesome everything will sound. So there's no physical way to visually see phase while mixing live. It is an ear training and critical listening skill. So practice it and recognize what it sounds like. It's very important to be able to identify when you're having phase cancellation or comb filters. Part of the reason is because it can cause discomfort or distraction, but more so if you're more in phase, the better everything will sound. It'll just sound really thin and hollow if it's out of phase. So why is it so important to know the 7 characteristics of a sound wave? Now, I mentioned this earlier, but we're going to talk about it again. The reason that you should be very familiar with the 7 characteristics of a sound wave is simply because if something doesn't sound right, If something is too loud, if something is causing pain or irritation, if it's causing distraction, it is going to be one of these things or more. The better you become at critical listening and the more familiar you become with the Big Seven, the better of an audio engineer you will be. You will become more proficient, faster, and more accurate than the other guys. It will help you stand out in a good way and help give confidence to your pastors and your worship leaders that you are the guy that they can depend on. And that's it for 7 characteristics of a sound wave. I hope you enjoyed this, and watch this video several times so you become very familiar with what they are. And a good engineer will know how to identify what the problem is. A great engineer will know how to identify it and fix it. And I'm hoping that you guys can be great engineers someday. And I look forward to standing next to you and mixing with you someday. All right. Thank you.
5, 4, 3,